All right, everyone. Hello, and welcome to the first screencast for Chapter 6. In Chapter 6, we're going to talk about a lot of the different things you can do with variables, which are sometimes referred to as dummy variables. There's some other names for them also, and we'll talk about those different names as we go through this chapter. So a dummy variable is just a variable that can take on only two values. It's either 0 or 1. Other names for dummy variables are dichotomous variables, binary variables, indicator variables. Sometimes when people talk about the distribution of such a variable, they'll talk about a Bernoulli distribution. But dummy variable, dichotomous, binary, indicator, that's mostly the terms you hear when talking about it in terms of a data set, in terms of rows and columns. And you have a column that is one particular variable, and that variable can only take on two values, 0 or 1. So for example, let's think about the effect of a team playing at home or away. So we could use a dummy variable for that, and we could code home games as 1, and we could code away games as 0. And if we did that, we would probably call that variable in the header of the data set, that column would be named home. And so that's very common with dummy variables, that the name of the variable itself is the category that gets the 1. So for home games, the home variable would be a 1, and for away games, the home variable would be a 0. So here is a data set of two crap teams from Manchester, England, Man United and Man City, that play in the English Premier League. And here we have the goal differential for each of those two teams, and it's been separated by all of the away games and all of the home games. All right, and so goal differential is just the number of goals you score minus the number of goals that were scored against you for a particular game. So we see all the different games here. Each dot is a game. If the game was away, then it's going to be get a 0. If the game was home, it gets a 1. And then on the vertical axis, you get the goal differential. And we can see here for both teams, the average for home games is higher than the average for away games, the average goal differential, that is. So for home games, Man City, on average, has a 1.37 goal differential, but for their away games, they only have a 0.32 goal differential. So these are both good teams. If you don't know a whole lot about English soccer, both of these teams are some of the top teams historically in the past 10 years. And so both of them have positive goal differentials, whether it's home or away. But we can see for both of them, the average goal differential for home games is higher, as is indicated here. So in this chapter, we're going to look at several ways we can use these types of variables to sometimes as independent variables of interest, and sometimes as controls. And so that's what this chapter is all about. So let's go back. We're going to go back to that example with Man United. Here we see Man United and Man City. We see some Man City supporters here. And we're going to look at using bivariate OLS to assess a difference in means test. So in this situation, what we're going to be doing is we're going to be conducting a type of statistical test that you've probably already used before in other stats classes, and it's just called a difference in means test. If I have two groups and I have some measure on those two groups, I want to know if the mean value for each group is really different. Is it statistically significant? Is the difference statistically significant, right? So, so that's what we're going to talk about in this screencast, this first screencast. So a difference in means test involves comparing the mean variable for one group to the mean of another. So for example, home games versus away games, the treatment group versus the control group, Democrats versus non-Democrats in different data sets. So I want to know, is there a difference in, say, goal differential between home games and away games? Is it statistically significant? Because we know, because of modeled randomness and sampling randomness, that we could see a difference that could be completely due to chance. And what the difference in means test allows us to do is to determine whether or not the difference that we observe is big enough, given the variance, that I can say that they're not equal to each other, that the average goal differentials for this first example is not the same. I can reject that. That's the way we're going to go about this difference of means test. And the great part is we don't have to develop a new mousetrap. We're going to just use OLS regression, because an OLS regression, a bivariate OLS regression, where the independent variable of interest, the right-hand side variable, is a dummy variable, is the same as a difference of means test. It functions the same way. So you may have done a difference of means test in another stats class, and you calculated the mean, and then you would go and you would find the standard deviation or the variance. Then you would go to some statistics table in the back of the book, and you would try to determine, can I reject the null hypothesis that these two values are the same? We're going to do the same sort of thing, but we're going to use the technology we already have developed. We already know how to determine if there is statistical significance in an OLS regression. So we're just going to use that. It's equivalent to doing it the manual way, by doing it with an OLS regression. So here's a way to think about it. Think about it as an experiment, maybe. Some people are given some treatment, and some people are not given the treatment. Those are the control group. So the control group gets a 0 for the variable. The treatment group gets a 1. If you think back to at the beginning of chapter 4, we talked about the anthrax medicine that was given, and so you could have coded that as a 1 and 0. In fact, I think we did that at the beginning of chapter 4. So the dummy variable here, I'm just going to be generic for a second, and then we're going to talk about some examples, is treatment. So treatment is the name of the variable. So in our data set, we have the value that we're comparing, and then we also have a variable called treatment. So the row in that data set gets a 1 for that column if it received the treatment, and it gets a 0 if the person didn't receive that treatment. So here is what the OLS model would look like. So here is our dependent variable. This is the thing I want to know if that variable differs across the two groups. What two groups? The group that got the treatment, the group that gets a 1 for that variable, and the group that didn't get that treatment, the group that gets a 0 for that variable. All right, so it's a very simple data set, 2 columns. Y is the measure that I'm interested in comparing, and then the treatment variable, that column, is whether or not the person got the treatment or not. So here is the regression for that. So notice for the control group, what is the value of treatment for them? All right. Well, for the control group, the value of treatment is 0. So if I was looking at the fitted value, and remember what the fitted value is. The fitted value is the predicted value of the dependent variable once I've estimated the regression, and I have beta naught hat, the intercept, and I have my beta 1 hat. So I run this regression, I get estimates for these two terms, the hats, and now I have this formula. And what I do is I'm going to plug in a particular value for the independent variable. Here it's 0 because everyone who didn't get the treatment got a 0. And I'm going to see what would be the fitted value for everyone who has a 0 for the treatment variable. So that's what I'm doing here. I plug in 0. 0 times anything is 0. So that's why that term disappears here. And so the predicted value for the control group, or for the group that gets 0 for the dummy variable, here the group that gets 0 for the treatment, their fitted value, my prediction about their dependent variable value would be the intercept. So notice, the intercept means something here. Up until this point, the intercept is only served to get us a good beta 1 hat. The only reason we have the intercept, the only thing we do with it is we say, oh, well, literally, sure, if the independent variable was 0, that would be the value of the dependent variable. But up until this point, we didn't put a lot of stock in whatever that number was that came to us from R, or that we see in a table of output. It's always there, the intercept. We even get a measure of statistical significance for it, but we never did anything with it really until this point. We never interpreted it, right? Now we can interpret it, because for this particular type of regression, a bivariate regression where the independent variable is a dummy variable, gets a 1 or a 0, the intercept is the predicted value of the dependent variable for everyone who gets a 0. So now it does have an interpretation. For the group that gets a 1, what is the fitted value? Well, my predicted value of the dependent variable, I just plug in 1 for the variable treatment here. And again, what are these beta naught hats and beta 1 hats? I ran this regression and I got the estimates from R, or whatever statistics program you're using. And so I plugged in those values, those numbers, and then I put in a 1 because that's the value of this independent variable for everyone who received the treatment. And so the fitted value for the group that got the treatment is beta naught hat plus beta 1. All right. So the interpretation here is a little bit different. We're going to interpret beta naught hat, and then when we want to know something about the group that receives the treatment, it's going to be a combination of these two values. And you'll see all of this maybe more clearly once we look at some specific examples. So just to summarize what we've done so far, for the control group, the fitted value or the predicted value of the dependent variable is the intercept, beta naught hat. For the treatment group, the predicted value is the intercept plus beta 1 hat. All right, that's going to be my prediction of the average value of the dependent variable for the treatment group. All right. Okay, so what is beta 1 then? Well, beta 1, notice, is the difference between the control group and the treatment group. Turns out that's the same exact way we've always interpreted beta 1 hat, right? Beta 1 hat is the effect of a 1 unit increase in the independent variable. What is a 1 unit increase in the independent variable here? It's being in the treatment group, right? So beta 1 hat has the same interpretation. It's the effect of a 1 unit increase in the independent variable. Here, because we have more context, it is the effect of being in the group that got a 1, all right? In being in the group that received a 1 for the treatment variable, or for the dummy variable to be more generic. So beta 1 hat is the difference in the average dependent variable between the treatment and control group, between the group that got a 1 and the group that got a 0. It's the same interpretation as before, which is why it's so nice to be able to use OLS regression for a difference of means test, because we already know what beta 1 hat means. That's the difference in the two groups, and we already know how to do the statistical significance of that difference, right? If beta 1 hat is positive or negative, we know that we possibly have a difference between the two groups. But we have to check whether or not we can reject the null that beta 1 hat is 0, right? I'm sorry, that beta 1 is 0. Because if beta 1 is 0, then there's no real statistical difference between the two groups. It's all very much analogous to what we've done so far. So if beta 1 hat is greater than 0, then the average value of the dependent variable is higher for the treatment group. If beta 1 hat is negative, then the average value of the dependent variable is lower for the treatment group than it is for the control group, or it's lower for the 1 group than the 0 group, right? Because we want to start thinking about how we would generalize this to other cases that aren't necessarily experimental treatment and control. And then if beta 1 hat is 0, then the average value of the dependent variable is the same for the treatment group and the control group. So here is a version of that for, let's see if I can get this all on the screen here. There we go. So this is what it would look like in the scatter plot. Now the scatter plot looks a little bit weird here, right? Because notice the x value, the value on the horizontal, can only be 0 or 1, right? So all of the dots in the scatter plot will have to line up either on the 0 or on the 1. Right? There's not going to be any dots over here, right? Because these dots would have a value for the dummy variable of like 0.8 or something. But that's not allowed. This variable only takes 1s or 0s, all right? And so you can see that this is very much like our scatter plot from before, even though we only have this weird looking scatter plot. The beta naught hat is the average for the control group. It's the intercept, all right? And the beta 1 hat plus beta naught hat is the average for the treatment group, or the group that has a 1 for the dummy variable. And beta 1 hat is the slope. It's the difference in the average for the two. And you can almost literally see it here. If I was to take this and subtract this away, all I would be left with is beta 1 hat. That's the difference. And it's the slope of the best fit line. It's a little bit weird looking best fit line, again, because of the binary nature of this variable, the dummy variable, but it still works in the same way. It still gives us the same information there. So we can use this method to compare any two groups. It doesn't have to be a randomized controlled experiment to compare means this way. All right. So here is some data from a feeling thermometer survey about President Obama from December of 2011. And let me see if I can put this up here. So I'm going to do feeling thermometer score for person I. So this is survey data. And the feeling thermometer score is going to be beta naught plus beta 1 times whether or not the person is a Democrat. And epsilon. So this is going to be a difference of means test that will tell us, let's see if I can erase, there we go. This is going to tell us whether or not Democrats have a systematically different feeling thermometer score for President Obama than do non-Democrats. And my guess is probably they do, right? One would guess that with partisanship, especially being as strong as it is now, that Democrats are probably going to have a higher feeling thermometer score, all right? What is a feeling thermometer score? I should go into that real quick. A feeling thermometer score is one way that people who do survey research gauge how people feel about particular things. You may have heard in marketing courses about a Likert scale where they say, please rate from, it's usually a 5-point scale or a 7-point scale. It usually goes from strongly disagree, slightly disagree, neutral, slightly agree. If it's a 5-point scale, sometimes it's 7. Feeling thermometer score is trying to get at something similar, but they tell people between 0 and 100, how do you feel about a particular politician or a particular policy? The idea here is that you give people more ability to express their preferences that is not so chunky, like a 5-point scale. Doesn't allow someone, there may be two people who both say on a 5-point scale, 1, 2, 3, 4, 5. Two people may say 3, but they may actually lean in one direction, but not enough to go to a 2 or a 4. With a 0 to 100 scale, it allows people to express more fine-grained feelings about that. But there are, of course, trade-offs. And if this was a survey research class, we'd talk about those trade-offs. But for now, we're just going to use it as our example. So again, feeling thermometer score 0 to 100. Democrat 1 if they are a Democrat, 0 if they are not a Democrat. All right, and one can imagine a big chunk of those non-Democrats are probably going to be people who consider themselves Republicans or Republican-leaning. All right, so there are two different ways to test the difference of mean, and they actually contain the same information. All right, in this first column, we have run this one. All right, so this, let me color code this. This is the blue column. And then let me see if I can get my color change to work. The other one is feeling thermometer score of person I, beta naught plus beta 1. But now the dummy variable is non-Democrat. So in the data set, for this one, if we use this version in the data set, the column non-Democrat gets a 1 if you're a non-Democrat and a 0 if you're a Democrat. And that's the results here in this column of the output. All right. And so you can run it either way. As it turns out, the result substantively, the actual meaning of the output is the same. You just have to remember which way you did it. right? And this is going to come up a lot, especially there's going to be things like gender. In many data sets, people either identify as male or female, especially historic data sets. There weren't a lot of other options that were presented by survey data. And so you can either run male 1 or you can run female 1. And as it turns out, the results will be the same. You just have to be careful when you go to interpret the output that you remember which thing did I give the 1, all right? Which category got the 1? So the left column here has X1 is 1 for Democrats, and the right column, the X1 gets 1 for non-Democrats. You wouldn't run this both ways unless it was for an example like this in a class. But what I'm going to show you here is that you don't have to worry too much about which category you pick as the 1. In some research, there's a natural way that you do it because of your particular question. It makes most sense for something to get a 1 and the others to get a 0, but it doesn't ultimately matter for this difference of means test. So the estimated results are negatives of one another. Notice for Democrat and non-Democrat, it's 41.82 and negative 41.82, but not for the constant, right? The constants are different, all right? So what's going on here, all right? Okay, so first thing to note is that the constant is always going to be the average value for the group that got a 0. So here, in this first column, the constant right here, this is the average feeling thermometer score for Obama for people who were not Democrats, all right? That's how you interpret the constant. Over here, change colors, this is the average feeling thermometer score for people who are Democrats, because in this version of the model, where non-Democrat equals 1, all right, the constant is the 0 category, the average of the dependent variable for the 0 category. So this is for the Democrats. So we can use the constant to find the average value for the treatment equals 1 group, all right? So first of all, let's press pause for a second. Let's just interpret this like it was a regular old regression, all right? So I'm doing this one right now. Let's switch to blue here. I'm doing this one first, all right? So first of all, is this statistically significant? Is the difference of the mean feeling thermometer score statistically significant? T is way, I could say way a million times here, bigger than 2. We can strongly reject the null hypothesis that the feeling thermometer score for the 1 category Democrats and the 0 category non-Democrats is the same. Beta 1 hat is statistically significant. What is beta 1 hat? It's the difference between the average feeling thermometer score for the 2 groups. So now we can interpret that. So on average, in our data set, Democrats had a 41-point higher feeling thermometer score for Obama than did non-Democrats. So beta 1 hat is the difference in the group that got a 0 non-Democrats and the group that got a 1 Democrats. But what is that? It's the same as it always was. Beta 1 hat is the effect of a 1 unit increase in the dependent variable. What is a 1 unit increase in being Democrat? It means going from being non-Democrat to being a Democrat. All right? So beta 1 hat is the difference between non-Democrats and Democrats. All right? And we can say it is very much statistically significant. So we already said here in the previous slide that this was the average feeling thermometer score for the non-Democrats, the group that got a 0. And in fact, probably most of those people are Republicans. But we're allowing, there could be third-party folks in there. So those people would also get a 0 if Democrat is the 1 variable. All right. So what is the average feeling thermometer score for Democrats? Well, remember, let me jump back here. If I can, there's going to be writing all over the screen, but try to ignore the writing because I want that to be there when I go back to talk to it. The average for the dependent variable is right here. You add together the 2 estimates, right? So the average feeling thermometer score for people who get 1 for the independent variable, the Democrats, is beta naught hat plus beta 1. So that's going to be roughly, let's see, 41.82, 23.38. That's going to be 65.20. Yeah, I just did that math in my head really fast. Actually, no, I didn't. It actually appears somewhere else. It turns out for the other version of the model, look right here what this is, 65.20. So this is the average in this model of the group that got a 0, right? What is that group? Well, it's the Democrats, right? So the average feeling thermometer score for the Democrats is 65.20. It just shows up as a number. We don't have to calculate it. What is this up here, all right? Well, this is the average difference between the non-Democrats and the Democrats, right? Here, non-Democrat is the 1, all right? So there is a 41.82 decrease as you go from being a Democrat, you got a 0 for this variable, to being a non-Democrat, you got a 1 for this variable. So notice these are symmetric. The difference between the mean feeling thermometer scores across the two groups is the same. It doesn't matter which way we run the model. So at times, you're going to want this to be an easy number to find. And so counterintuitively, you put the group you don't really care about as you put the group that you care about as the 0 group. All right. So if you're really interested in the effect on Democrats, you might actually run this model. All right. Both models will tell you the difference between the groups, but this model over here tells me directly what the average feeling thermometer score is for Democrats. Now, I can still recover what the average for non-Democrats is for the 1 group here. I just add together beta 1 hat right here and beta naught hat. So negative 41.82 plus 65.20 is, that's right, 23.38. It showed up over here, all right? So you don't have to worry too much about which version you run. The information that you're getting from this difference in means test is the same. And here's what this looks like for this particular regression. What I've done here, and I note this over here, is remember the non-zero, the X value, non-Democrat or Democrat. Here, this is the Democrat equals 1 version. All right, I'm sorry, let me change that. I had that in blue, that version of the model, so let me just be consistent. This is the Dem equals 1 version of the data set, all right, where there's a variable called Democrat, and everyone who was a Democrat got a 1 for that column, and everyone who was a non-Democrat got a 0 in that column, all right? So, but notice, well, what's going on here? What is this, a negative 0.1? Is that scatter plot dot right there a negative 0.1? No. It's pretty common when you're dealing with binary variables or dummy variables to do what's called jitter the data for display purposes. So basically, it just gives it a little random shake when plotting. It doesn't change the data in the data set. In the data set, we'd still see a column. We would still, let me put this back just so I don't forget. In the data set, we would still just see a column called Dem, and that column is still just going to have 1s and 0s, all right? It's not going to jitter the actual data. But for display purposes, before it's plotted, you can call a jitter command in any stats program you want, just so we can see the volume of data, right? If all of these were forced to have a 0 as their x coordinate, we wouldn't really see how much volume of the dots is down here and how much of the volume of the dots is up here for the Democrats, right? So by jittering, we get a better visual representation of where the mass of the data is, all right? And so we're going to see this throughout this chapter where we're going to jitter the data when we display it just so we can see it better, right? So that all the dots aren't showing up right on top of one another, and in which case we can't really tell how many of them there are. So a 1 unit change in x is associated with a beta 1 hat, the slope, the beta 1 hat difference in the two groups, or the effect of going from being in the 0 group, the non-Democrats, to the 1 group, being a Democrat. All right, so let's look at another example that's maybe a little bit more, has a little bit more texture to it. And so this is going to be looking at the differences in height across by sex, all right? So here we're going to look at the difference of means test for gender. Here gender and sex are equivalent for this particular data set and this example. And this is probably one you did, even in maybe high school or even junior high. Middle school, sorry, I'm old. Junior high was what we had. Even in middle school, one of the first basic statistical things you do is you gather some data about your class and you say, is it different between girls and boys, right? That's an obvious one that is easy for everyone to think about and calculate, right? So in this sample, everyone is identified as either male or female, and we're going to have their heights, and we're just going to do a simple difference of means test. But we're not going to have to do the manual calculation. Go look it up in the back of the book. Check the Z, T, F, whatever table that your teacher told you that you had to memorize, and then looking to see if it's statistically significant. We're going to use our friend OLS regression because we already know it well by this point. So here is what the data for this particular data set looks like. And again, this has been jittered, right? Because the data set can only take a 0 or 1 here. But in order to see the data better, right, all of these dots would have been masking themselves, masking one another. All of these dots, a lot of them would have been masked. We wouldn't have been able to see just how many of these dots there are unless we had jittered them, all right? So here's what the data looks like. And what we want to know is there a statistically significant difference, right? Why? Because it's a sample, right? And I don't think there's probably too much modeled randomness in height. Height doesn't really vary a ton across different days, but you could get a sampling issue, right? If this is the differences in, say, a particular class of students or students at a university, right? On the day you took the measure, your sample may not have been representative of the whole, sometimes because people just weren't there on that day or whatever it is. So is the difference statistically significant, right? What if I took a sample and for a lot of the males, I got a whole bunch of the basketball players or something, right? There's an overrepresentation of people who are generally taller than average, right? I need to have a standard error and I need to be able to convert that into a t-test. Thankfully, R is going to do all of that for us. And then I need to be able to look at that t-test or p-test and say, does it meet our threshold for statistical significance? And we can use all of the same tools we've already learned. So here is what this regression looks like. And again, in this data set, there's either, everyone identified as either male or female. So we're going to first look at the version where the independent variable of interest is male. All right, so male got the 1 in this data set, and everyone who didn't identify as male, there's a 0. All right, so this is the regression we run first, and here is what we get back. All right, so we get back a constant of 64.23. Normally we just go, okay, yeah, constant, let me move on down to the actual coefficient, the slope coefficient, but now the constant means something for us. And also we have the slope coefficient. So first things first, what do we always check first? Is it statistically significant? What is this beta 1 hat? What is it measuring? It's always the 1 unit increase in X. What is a 1 unit increase in X here? It's going from being non-male to male, or going from being in the non-male category to the male category. What is the difference in the independent variable across those two groups? So that is statistically significant, that difference. So, I mean, this is way bigger than 2, so I can reject the null that the height across the average height across the two groups is, the difference in the average height across the two groups is 0. I can reject that null. So now I can go and interpret this. So on average, the males in our sample, 5.79 inches taller than the average female in the data set. All right. What is the constant? How can we interpret that? Well, the constant is the average for the group that received a 0 for the independent variable in this difference of means test. So that's the non-males. So the average height for non-males is 64.23. What if I want to know the average height of the males? Well, there's where I have to do a little bit of work. I have to add the beta naught hat plus the beta 1 hat. So that's going to be, what, 69, 70-ish, right? And I already have it calculated here on the next slide. So 64.23 inches is the average height for the women, and 70.02 is the average height for the men. The difference is 5.79. And we could have gotten the same exact information if we had run a version with female as the one. So here is what this looks like. Here's the average height for males, the average height for females, and then the difference is the slope. And so the slope would look something like that. The slope of that line is the measure of the difference in the average between the two groups. So we know the difference of means is 5.79, but we didn't really need a regression to tell us that, right? We had the data sets originally. We could have averaged all the males' heights, averaged all the non-males' heights, and found the difference, right? So why are we going through all this linear regression? It's because of the statistical significance part. That's the part that's a pain when you do the old school difference of means test, right? You have to go and do all the looking up on the table thing. But now we get it as part of the results. The output from R will give us a t-test or a p-test. In fact, it gives us both. And we can see right here that we can reject the null, that the average, the means of the two groups are the same. There is a difference in the means in this difference of means test, all right? So that's what using a regression buys us here in this difference of means. So the t-statistic is 103.4, so we can reject the null big time. We can also calculate, just like we did before, a 95% confidence interval. If you go back to chapter 4, if you want to see the calculations on that, and the average, the difference between the two groups, the 95% confidence interval is from 5.68 to 5.90, given the variance in our sample, given the spread of our the spread of our dependent variable. So over here, I've done the other version of the model, right? I've run it with female as the variable that gets 1, and non-females gets 0, all right? And so here we see, notice the difference of means, notice the statistical significance is exactly the same, right? It's because these are mathematically coming from the exact same information. The difference between the two groups is the same. Here, the males were on average 5.79 inches taller. Here, the females on average are 5.79 inches shorter. And because there's only two groups in this data set, those are mirror images of one another. Now, what is different is the intercept. Remember what the intercept was over here? This is the average for the 0 group. In this version of the model, that was the non-males. Over here, the 0 group, the group for the female variable that got a 0 were the non-females. And their average height is 70.02. If I add these two together, if I add the difference in heights to the average heights of the non-females, I get 64.23, the average height for males. Notice, the average height for the females, right? The constant is, yes, I add this constant, which is the average for the non-females, to this one, which is the difference, and I get this number here. So again, it doesn't matter which way you run the model. So don't worry too much about, am I coding this variable as a 1 or a 0? The information is the same in a difference of means test. You get the same information. You just have to be careful when you're interpreting it to remember which category got the 1, right? Because this is going to be the average for the category that got the 0 in the dummy variable regression or the difference of means test. Both contain the same information. You can run it either way. Difference of means tests only tell us there's a statistically significant difference in the mean value of a dependent variable across two groups, but it's still just a simple correlation. Endogeneity could still be huge here. So we would never put any causal interpretation to this, right? that being male causes you to be taller, right? We would still have to think through omitted variable bias. We'd still have to think through endogeneity for our particular context of that, where we got that data and why we're running that test and what our research question is. But in terms of a really fast way to do a difference in means test, this really is way better than the old way that you may have learned in a basic stats class. We get to use all the same technology. The interpretation of beta 1 hat is exactly analogous. It's the difference, but it's a 1 unit increase, which is a going from not being in the group to being in the group. So it is very helpful. And the big bonus is the measure of statistical significance is interpreted in exactly the same way. Pick your poison, t-value, p-value, whatever you want to do, however you like to roll, the interpretation is the same. We can reject the null that beta 1 hat, the difference between the two groups, is 0 if t is bigger than 2 or 1.96, or if p is smaller than 0.05 if we're using a level of significance of 0.05. So providing evidence of causality on a binary x and y requires us to deal with that omitted variable bias. In social science and business statistics, a statistically significant difference of means is a question or a puzzle. It's not usually our answer, right? If I look at two different groups in society and some dependent variable for those two groups is different, right? Well, that's a puzzle. That's a question. Why would it be different for those two groups, right? If I look at, say, income for males and females, and I see a statistically significant difference, I haven't shown anything causal whatsoever, right? I would have to do all of my omitted variable bias work. I would have to do all my endogeneity questions to determine, is it because they are women that they make less, right? That's the wage gap that you've probably heard about in other classes. Or is there something else going on, right? And there's a lot of work on this in labor economics, and I can just share with you that really quickly. A lot of the difference does go away when you control for other things, but there's still a chunk of the difference that does not go away. And it's been getting smaller, especially for younger women, than it is for women who've been in their careers for 30, 40 years. Back when sexism was a much bigger problem, thankfully. Not that it's gone away completely. But anyways, the point here I was trying to make is that when you see a difference using a binary regression with a dummy variable, and you get a statistically significant beta 1 hat, for us in social science and business, that's usually that's the beginning of the project. So, well, why am I seeing a difference? You cannot attribute causality to that, right? And people fall prey to this all the time. They look at two groups in society, they see statistically significant differences in some outcome, and they say, oh, it's because of this, the variable that they differ by, right? It's because they get a 1 for that category that they're in. And you've shown no such thing. You've shown no such thing. All you've done is shown that there is a statistically significant difference, but you haven't shown that it's causal in any way. All right, so don't fall prey to that. Even sometimes I see professors falling prey to that. I see a difference between two groups, and I'm going to attribute their membership to a particular category as what is causal, and it's just not the case at all. It's a fundamental statistical error that they're making. Okay, so that is the end of section 6.1, and so I'm going to pick it up in just a second, or maybe not a second. You might take a couple days. Whenever, I'm going to move into section 6.2, and we're going to look at other things we can do with dummy variables. All right, it's not just for a bivariate, one independent variable, one dependent variable regression, where we're doing a difference in means test. All right, we can use dummy variables for other things. Primarily in this class, we're going to be dealing with dummy variables on the right-hand side of the regression. Dummy variables on the left-hand side, that's really something beyond the scope of the class. If you have that for your paper, I can talk with you one-on-one about some things you need to be careful about with that. But in general, we're going to be looking at right-hand side independent variables or control variables with 1s and 0s. All right, that's it for 6.1.